Now in this lecture we find out the area of the small circle. In the drawing we have a semicircle. Note that line segment AQ equals to 2 units in its length, line segment TB equals to 8 units in its length. This is angle PQA, that is a right angle. This is angle STB, that is also a right angle. Inside this semicircle we have this circle, and our mission is to find out the area of this small circle. Okay, so first of all we will define the relevant points to this question with letters. We will define the center of this big semicircle, this point, as point H. We define the center of this small circle, this point, as point K. We will define the point of tendency of tangent ST with this small circle, this point is point L. And define the point of tendency of tangent PQ with this small circle, this point is point Y. And finally, we define the point of tendency of this tangent AB with this small circle, this point is point M. Here we can implement rule 3. According to rule 3, the sum of the angles on one side of a straight line is equal to 180 degrees. Okay, so AB, this is side AB. It is the diameter of this semicircle, therefore it is absolutely a straight line. So AB is a straight line. If we focus on the upper side of this straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB at point Q? We have this angle that is a right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. We continue to focus on the upper side of the straight line AB at point T. And the upper side of AB at point T, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB at point T? We have this angle that is right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. We will join points K and M together by a straight line. What is the definition of line segment KM? Line segment KM starts from point K, that is the center of this small circle, and ends at point M, that is the point of the small circle itself. This is exactly the definition of a radius. Therefore Km is the radius of this small circle. We define the radius of this small circle as x, therefore Km equals to x, according to our definition. Here we can implement rule 1. I'll repeat quickly on rule 1. According to rule 1, A tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing we have a circle and we have tangent AB. This is tangent AB that is tangent to this circle at this point, point M. And we have the radius OM that equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule, all 1. So, we can actually implement all 1 in our drawing. In our drawing, we have the radius Km that is equal to x. The radius Km is drawn to point M, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MK. If AB is perpendicular to MK, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. We join points K and Y together by a straight line. Line segment YK is of course the radius of this small circle, that is equals to x according to our definition. So here again we have the radius Ky that is on the point Y, that is the point of tendency of tangent PQ with this small circle. And whenever your radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius YK. If PQ is perpendicular to YK, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we'll focus on the small quadrilateral YKMQ. In the small quadrilateral YKMQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral YKMQ, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be just a rectangle if not a square. So we relate to this small quadrilateral YKMQ as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle YKMQ, side YK must be equal to the opposite side MQ. But YK is x, therefore MQ must be also equal to x. Likewise, according to the same rule, in the same rectangle YKMQ, side KM must be equal to the opposite side YQ. But KM is x, therefore YQ must be also equal to x. So actually found out that the small quadrilateral YKMQ is not a rectangle but a square. Why? Because of the fact that all 3 sides of this square are equal to each other. Each side of this square is equal to x. So I write it down. Quadrilateral YKQM is a square. In the next step, we'll join points K and N together by a straight line. KL is of course the radius of this small circle is equal to x according to our definition. Again, we have here the radius KL that is drawn to point L, that is the point of tendency of tangent ST with this small circle. And whenever your radius that is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LK. If ST is perpendicular to LK, it means that this angle equals to 90 degrees. And and this angle also equals to 90 degrees according to rule 1. So inside the small quadrilateral KL edge M, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees according to the rule that the sum of the areas in any quadrilateral is equal to 360 degrees. Therefore this 4 facing angle must be equal to 90 degrees in its size. So inside the small quadrilateral KLTM, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be just a rectangle, if not a square. So we relate to this small quadrilateral KLTM as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle KLTM, side KL must be equal to the opposite side TM. But KL is x, therefore TM must be also equal to x. Likewise, according to the sum rule, in the sum rectangle KLTM, side KM must be equal to the opposite side LT. But KM is x, therefore LT must be also equal to x. Again, we should found out that quadrilateral KLTM is not a rectangle but a square. Why? Because all of its sides are equal to each other. So I write it down. This quadrilateral KLTM is a square. We have here angle. This is angle YKL. Angle YKL, the size of angle YKL equals to 90 degrees plus 90 degrees, that is 180 degrees. Again, angle YKL equals to 180 degrees in its size. And we know that any angle that is equals to 180 degrees in its size, it is defined as a straight line. Therefore, YKL is a straight line. YKL is a straight line. But YKL is a straight line that touches the circle at 2 points, Y and L. Therefore, YKL is a chord, because any straight line that touches the circle at 2 points, it is defined as a chord. So we have YKL is a chord, but YKL is a chord that passes through point K, that is the center of this small circle. And we know that any chord that passes through the center of the circle, it is the diameter of the circle. So therefore, YKL is the diameter of the small circle. So if YKL is the diameter of the circle, it means that YL is the diameter of the circle. So, okay, YL is the diameter of the circle, so I'll write it down. Line segment YL is the diameter of the small circle. Okay. But what is exactly the definition of shape YL TQ? What is the definition of this shape YL TQ? First of all, YL is the diameter of the small circle, therefore it is absolutely a straight line. So inside the shape YL TQ, we have 1, 2, 3, 4 sides, and therefore this shape YLTQ is a quadrilateral because it has 4 sides. Inside quadrilateral YLTQ we have 1, 2, 3, 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle, if not a square. So we relate to this quadrilateral YLTQ as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle YLTQ, side YL must be equal to the opposite side qt. But yn is x plus x, that is 2x. It is actually the diameter of the small circle. This small circle is equals to 2x. So yn is 2x, therefore qt must be also equal to 2x. So this side qt must be equal to 2x. So I'll write it down. So this is side qt, that's equals to 2x units in its length. Repeat again. This is side qt, that's equals to 2x units in its length. In the next step, we'll find out the radius of this big semicircle. What is the radius of this big semicircle? First of all, we'll define the radius of this big semicircle as capital R. So what is the value of capital R? Capital R equals to the diameter of this big semicircle, that is AB over 2. Repeat again. So the radius of this big semicircle equals to capital R, and capital R equals to the diameter AB over 2. So what is the length of the diameter AB? From the moment it's very easy to see that AB in total equals to 2 plus 2x plus 8. So AB in total equals to 2 plus 8, that is 10 plus 2x. Again, AB in total equals to 10 plus 2x. So I write it down. We found out actually that the diameter AB of this semicircle equals to 10 plus 2x, and the diameter over 2 is the radius capital R of the semicircle. So the diameter capital R equals to 10 plus 2x over 2. 10 plus 2x over 2 equals to 10 over 2, that is 5, plus 2x over 2, that is x. So in total, actually found out the diameter capital R of the semicircle equals to x plus 5 units in its length. Repeat again. The radius, actually found out that the radius of this big semicircle, capital R, equals to x plus 5 units in its length. What is the length of this missing side, edge M? The length of the missing side, edge M, must be equal to A edge, that is the diameter of the semicircle, that is equals to x plus 5. So it is A edge minus AQ, that is 2, minus QM, that is x. So total, the missing side edge M here equals to A edge, that is the radius of the semicircle. Again, A edge is the radius of this semicircle, minus AQ minus QM. Repeat again, the missing side edge M, from the drawing it's very easy to see that edge M, the missing side edge M equals to A edge, that is the radius of the semicircle, that is equals to x plus 5, minus AQ. AQ equals to 2, minus QM. QM equals to x. So in total, edge M, the missing side edge M, equals to x plus 5 minus 2 minus x. X minus x is 0, so x will get cancelled, and 5 minus 2 is 3. So actually found out that the missing side edge M equals to 3 units in its length. this is the missing side edge M, that is equals to 3 units in its length, so I write it now. So here in the drawing, the big semicircle touches this small circle at this point. Again, the big semicircle touches this small circle at this point. That is to say, those two circles have an internal notch between them at this point. That is to say, they are touching each other internally at this point. And whenever you have an internal notch between two circles, you can implement rule 9. I'll repeat quickly on rule 9. If two circles touch each other internally, then the straight line that connects the centers together passes through their touching point. In the drawing we have this big circle touches this small circle at this point. Point P is their touching point. They touch each other internally at point P. And therefore, according to this rule 9, the straight line that connects the centers together is OM. Why? Because O is the center of this big circle and M is the center of this small circle. Again, the straight line that connects the centers together is the straight line OM. And according to this rule 9, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass through point P, that is their touching point, or OMP is one straight line. Again, OMP is one straight line according to this rule 9. We can actually implement rule 9 in our drawing. Why? Because in our drawing, the small circle is not just the big semicircle internally at this point. Therefore, according to rule 9, the center of the big semicircle is here at point H. The center of this small circle is at point K. And the straight line that connects the centers together is of course the straight line HK. This straight line HK must pass from this point, that is their touching point, according to rule 9. So I connect point H and K together by straight line, and according to rule 9, the straight line HK must pass from this point, that is their touching point. You can see from the drawing that the straight line HK passes for their touching point, that is this point. We will define their touching point, this point, as point D. Repeat again, from the drawing it is very clear, it is very easy to see that the straight line HK passes from point D. Oh, DKH is one straight line. Again, DKH is one straight line according to rule 9. If DKH is one straight line, it means that DH is a straight line. Again, if DKH is one straight line, it means that DH is a straight line. But what is exactly the definition of the straight line HD or DH? The straight line HD starts from point H, that is the center of this semicircle, and ends at point D, that is the point on the semicircle itself. So this is exactly the definition of our radius. Therefore AD, HD, this straight line HD is the radius of this semicircle. It is equals to x plus 5 units according to what we have already found out. So HD equals to x plus 5, the radius of the big semicircle. Likewise, what is the definition of line segment KD? Line segment KD starts from point K, that is the center of this small circle, and ends at point D, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, dk is the radius of this small circle, that is equals to x according to our definition. So dk equals to x. So what is the value of the missing side k edge? The missing side k edge must be equal to edge d minus kd. Again, edge d minus kd equals to the missing side edge k. So I write it down. The missing side edge k equals to edge d minus dk. So the missing side edge k equals to edge d. Edge d is the radius of the big semicircle. That is equals to x plus 5 minus dk. dk is the radius of this small circle. That is equals to x. So in total we can find out that hk equals to x plus 5 minus x. X minus x is 0, so we left only with 5. In conclusion we can find out that the length of the missing side hk is equal to 5 units in its length. Okay. This is the missing side hk. This is equal to 5 units in its length. In the next step, I'll copy the right green triangle edge km in a new page, and we will implement the Pandara's theorem on this right green triangle edge km. According to the Pandara's theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pandara's theorem. The hypotenuse kh equals to 5. Side km equals to x, it is the radius of the small circle. And mh equals to 3. So this is the right green triangle KMH that I copied from the original drawing. According to the Pandara's theorem, in this right triangle KMH, KH square equals to KM square plus MH square. Again, KH square equals to KM square plus MH square. So I write it down. According to the Pandara's theorem, in this right triangle KMH, KH square, that is the square of the hypotenuse, must be equal to Km square plus Mh square. The hypotenuse kh equals to 5, therefore kh square is 5 square, that is 25, and it is equals to km square. Km is x, therefore km square is x square, plus mh square. Mh is 3, therefore mh square is 3 square, that is 9. So in conclusion, we can find out that according to the Pandara's theorem, 25 equals to x square plus 9. We subtract 9 from this equation, and you get that 25 minus 9 is 16. So 16 equals to x square. We can find out that x square equals to 16. x is the radius of this small circle. Therefore, x squared is the square of the radius of this small circle. That is equals to 16 units. Our mission is to find out the area of this small circle. We know that the area of any circle is equals to pi times the radius of the circle squared. Repeat again. The area of any circle equals to pi times the radius of the circle squared. Therefore, the area of the small circle, that is the area that we are looking for, must be equal to pi times the radius of the small circle squared. The radius of the small circle is x, therefore the radius squared is x squared. In conclusion, we found out that the area that we are looking for, that is the area of the small circle, equals to pi x squared. But we just right now found out that x squared equals to 16, so we can substitute x squared in this equation by 16. We do it now, and we get that the area of the small circle equals to pi times 16, or 16 pi. Repeat again. We actually found out that the area of this small circle, that is the area that we are looking for in this question, equals to either 16 pi square units, or in terms of numbers, it is equals to 50.265 square units. And that is the answer to the question. The area of this small circle equals to either 16 pi square units, or in terms of numbers, it is equals to 50.265 square units. Okay, so in the next step, I will summarize the lecture. In this lecture, we found out the area of this small circle. So in the drawing, we have a big semicircle. We know that line segment AQ equals to 2 units in its length, line segment TB equals to 8 units in its length. This is the angle PQA, that is a right angle. This is the angle STB, that is also a right angle. Again, inside this big semicircle, we have this small circle, and our mission is to find out the area of this small circle. Okay, so first of all, we defined the relevant points to this question with letters. We defined the center of this big semicircle, this point H. We defined the center of this small circle, this point as point K. We defined the point of tendency of tangent AB with this small circle, this point as point M. We define the point of tendency of tangent PQ with this small circle, this point is point Y. And we define the point of tendency of tangent ST with this small circle, this point is point M. And finally, we define the touching point of the big semicircle with this small circle, this point is point D. Okay, so here AB is the diameter of this semicircle. So AB is the diameter, it is absolutely straight line. Again, AB is the diameter, it is absolutely straight line. So here we can implement rule 3. According to rule 3, the sum of the angles on one side of a straight line is equals to 180 degrees. In our drawing, it means that the sum of the angles on the upper side of the straight line AB at point Q must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB at point Q? We have this angle, that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, if we focus on the upper side of AB at point T, here the sum of the angles must be equal to 180 degrees according to the same rule, rule 3. So which angles we have at the upper side of AB at point T? We have this angle, that is the right angle, plus this missing angle. In total, they must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. Okay. In the next step, we join points K and F together by straight line. What is the definition of line segment KM? Line segment KM starts from point K, that is the center of this small circle, and that's at point M, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore Km is the radius of this small circle. We define the radius of this small circle as x, therefore Km equals to x. So here we can implement rule 1 because we have the radius Km that is drawn to point M, that is the point of tendency of tangent AB with this small circle. Whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MK. If AB is perpendicular to MK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points K and Y together by a straight line. Line segment KY is the radius of this small circle. This is equal to x. So we have here the radius KY that is drawn to a point Y, that is the point of tendency of tangent PQ with this small circle. And whenever your radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius YK. If PQ is perpendicular to YK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So by doing this construction, actually created here quadrilateral YKMQ. Inside this small quadrilateral YKMQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral YKMQ we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this right angle, if not a square. So we relate to this small quadrilateral YKMQ as a right angle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle YKMQ, side YK must be equal to the opposite side MQ. But YK is x, therefore MQ must be also equal to x. Likewise, according to the same rule, in the same rectangle YKMQ, side KM must be equal to the opposite side YQ. But KM is x, therefore YQ must be also equal to x. So actually found out, finally, that quadrilateral YKMQ is not a rectangle but a square, because of the fact that all 3 sides are equal to each other. Each side of this square equals to x. So quadrilateral YKMQ is a square. Likewise, we join points K and M together by a straight line. KL is the radius of this small circle, that is equal to x. Again, the radius KL is drawn to point L, that is the point of tendency of tangent ST with this small circle. Whenever your radius that is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LK. If ST is perpendicular to LK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral KLTM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral KLTM, we have 4 right angles, therefore we can relate to this quadrilateral KLTM as a rectangle. But you also know that the opposite sides of rectangle are equal to each other. So a rectangle KLTM, side KL must be equal to the opposite side TM. But KL is x, therefore TM must be also equal to x. Likewise, according to the same rule, in the same rectangle KLTM, side KM must be equal to the opposite side TL. But KM is x, therefore TL must be also equal to x. So we found out that quadrilateral KLTM is not a rectangle but a square because of the fact that all of its sides are equal to each other. So we have here 2 squares. This is the first one and this is the second one. In the next step, we focus on angle YKL. The size of this angle YKL equals to 90 degrees plus 90 degrees, that is 180 degrees. So angle YKL equals to 180 degrees in its size, and we know that any angle is equal to 180 degrees must be a straight line. Therefore, YKL is a straight line. Again, YKL is a straight line. If YKL is a straight line, it means that YL is also a straight line. YL is a straight line that touches the circle at 2 points, Y and L. Therefore, YL is a chord. YL is a chord that passes through point K, that is the center of this small circle, and we know that any chord that passes through the center of the circle must be the diameter. Therefore, YL is the diameter of this small circle. I repeat again, we shall find out in conclusion that YL is the diameter of the small circle. Okay? So YL is the diameter, it is absolutely a straight line. So in shape YLTQ, we have 1, 2, 3, 4 sides. Therefore, shape YLTQ is a quadrilateral. Okay, again, shape YLTQ is a quadrilateral. We have one because we have 4 sides. This quadrilateral consists of 4 sides. This shape YLTQ consists of 4 sides, and therefore this shape YLTQ is a quadrilateral. Inside quadrilateral YLTQ, we have 1, 2, 3, 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral YLTQ is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle YLTQ, side YL must be equal to the opposite side TQ. But YL equals to x plus x, that is 2x. Is equal to 2x. It is actually the diameter of this small circle. Therefore, TQ must be also equal to 2x. Again, TQ equals to 2x. Now, we found out that QT of TQ equals to 2x. So, in the next step, we find out the radius of this big semicircle. What is the radius of this big semicircle? Actually, the radius, first of all, we define the radius of this big semicircle as capital R. So capital R will be equal to AB, that is the diameter, over 2. Again, the radius of this semicircle that is equal to capital R according to our definition will be equal to AB, that is the diameter of this semicircle, over 2. Repeat again. The radius of the big semicircle that is equal to capital R according to our definition will be equal to the diameter AB over 2. What is the length of the diameter AB? From the drawing, it is very easy to see that AB in total equals to 2 plus 8 plus 2x. 2 plus 8 is 10 plus 2x. So in total, the diameter AB equals to 10 plus 2x. Then the diameter AB equals to 10 plus 2x, and therefore the radius equals to AB over 2. That is to say, it is 10 plus 2x over 2. 10 plus 2x over 2 is 10 over 2, that is 5, plus 2x over 2, that is x. So in total, we found out that the radius of this big semicircle, capital R, equals to x plus 5 units in its length. Again, capital R equals to x plus 5 units in its length. Okay, the radius of this big semicircle equals to x plus 5 units in its length. What is the length of this missing side MH? From the drawing, it is very easy to see that MH in total equals to AH minus AQ minus QM. Again, AH minus AQ minus QM equals to MH. Repeat again. The missing side HM equals to AH minus AQ minus QM. AH is the radius of this big semicircle, that is equals to x plus 5. AH equals to x plus 5. Minus AQ. AQ equals to 2. So it is minus 2 minus QM. QM equals to x. QM equals to x. So in total, we shall find out that the missing side HM equals to x plus 5 minus 2 minus x. X minus x is 0, and 5 minus 2 is 3. Again, x minus x is 0, and 5 minus 2 is 3. So in total, we actually found out that the missing side NGM equals to 3 units in its length. Repeat again, this is the missing side NGM that equals to 3 units in its length. So here we can actually implement rule 9. Why? Because we have an internal notch between the big semicircle and this small circle. That is to say, they are touching each other internally. At this point D is their touching point. And whenever you have an internal notch between two circles, you can implement rule 9. I'll repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. We have here in the drawing two circles. Actually, they touch each other internally at this point P. The center of the big circle is 0.0. The center of this small circle is 0.m. And the straight line that connects their centers together is, of course, the straight line OM. And according to this rule 9, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass through point P, that is their touching point. Or OMP is one straight line. Again, OMP is one straight line. So we can actually implement rule 9 in our drawing. Why? Because in our drawing we have internal notch between the big semicircle and this small circle. That is to say, they are touching each other internally at this point D. And therefore, according to rule 9, the center of the big semicircle is 0.8. The center of this small circle is 0.k. And the straight line that connects the centers together is the straight line HK, and this straight line HK must pass through point B, that is their touching point. The straight line HK must pass through point D, that is their touching point. Or HKD is one straight line. Again, HKD is one straight line, according to rule 9. If HKD is one straight line, it means that HD is also a straight line. HD is a straight line, but what is exactly the definition of the straight line HD? The straight line HD starts from point H, that is the center of this big semicircle, and ends at point D, that is the point of the big semicircle itself. This is exactly the definition of a radius. Therefore, HD is the radius of this big semicircle, that is equals to x plus 5. Repeat again, we actually found out that the straight line HD is the radius of the big semicircle, that is equals to x plus 5. Yeah, the radius of the big semicircle equals to x plus 5. So HD equals to x plus 5. What is the definition of line segment KD? Line segment KD starts from point K, that is the center of this small circle, and then at point D, that is a point on the small circle, on this small circle itself. So KD is the radius of this small circle, that is equal to x. Again, KD or DK equals to x, it is the radius of the small circle. So what is the length of the missing side HK or KH? KH equals to DH minus DK. Again, KH equals to DH minus DK. And again, KH or HK equals to DH minus DK. So KH equals to HD, that is x plus 5. It is the radius of the big semicircle, that is equals to x plus 5, minus DK. DK is x. So in total, HK equals to x plus 5 minus x. X plus 5 minus x equals to x minus x is 0, so left only with 5. In conclusion, we found out that this missing side KH equals to 5 units in its length. In the next step, I copied the right green triangle KM edge in a new page, and we implemented the Pythagoras theorem on this right green triangle KM edge. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Actually, this is the right green triangle KM edge, with the common from the original drawing. The hypotenuse KH equals to 5, MH equals to 3, and KM is the missing side, is equals to x. This is actually the radius of the small circle. According to the Pythagoras theorem, in this right triangle kh squared equals to km squared plus mh squared. Again, kh squared equals to km squared plus mh squared. Kh is 5, therefore kh squared is 5 squared, that is 25, and it is equals to km squared. Km is x, therefore km squared is x squared, plus mh squared. Mh is 3, therefore mh squared is 3 squared, that is 9. In conclusion, we found out that according to the Pythagoras theorem, 25 equals to x squared plus 9. Here we subtracted 9 from this equation, and finally found out that x squared equals to 25 minus 9, that is 16. So x squared equals to 16 units. Our mission is to find out the area of this small circle. And we know that the area of any circle equals to pi times the radius of the circle squared. Again, the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of the small circle will be equal to pi times the radius of this small circle squared. The radius of this small circle is x, therefore the radius squared is x squared. So in total, we found out that the area of the circle, of the small circle, equals to pi x squared. But we just found out that x squared equals to 16, so we can substitute x squared in this equation by 16. We did it, and we finally found out that the area of this small circle equals to either 16 pi square units, or in terms of numbers, the area of this small circle equals to 50.265 square units. Repeat again, the area of this small circle equals to either 16 pi square units, or in terms of numbers, it is equals to 50.265 square units. Okay, thank you very much.